Good afternoon, respected session chair, co-chair, and participants. My name is Dr. Ibrahim Al-Najati, and today I'm pleased to present our research titled Thermal Efficiency of Polystyrene Filled Concrete Blocks in Residential Buildings, a case study in Al-Umara city. I would also like to thank the Conference Scientific Committee and Southern Technical University for organizing this important event. Before I begin, let me briefly walk through the structure of this presentation. I will start with a short introduction to highlight the motivation behind this work. Before I begin, let me briefly walk through the structure of this presentation. I will start with a short introduction to highlight the motivation behind this work and the energy challenges facing residential buildings in hot climates. Next, I will present the research objectives which define the scope and direction of our study. After that, I will explain the wall system and material characteristic, focusing on the three construction types we evaluated. This will be followed by the simulation setup, where I will describe the software, climate data, and key modeling assumptions used in the EQuest software. Then I will introduce the building model, including its geometry, thermal zones, and physical parameters. Following the methodology, I will present the main findings, starting with the monthly total energy consumption and then detailed energy consumption by the end user category, including heating and cooling loads. Finally, I will conclude with the main outcomes of the research and highlighting some future work related to the economic and environmental assessments. Buildings today consume more than 1/3 of total global primary energy. In hot regions, this share becomes even higher. In Iraq, especially in the southern provinces, more than 60% of residential energy is consumed in summer, mainly due to cooling. The dominant reason is the poor thermal performance of building envelopes, which leads to excessive heat transfer into indoor spaces. Therefore, improving the thermal characteristics of wall, roofs, and windows is the major challenge for reducing energy consumption. Our work focuses especially on improving external wall systems since they represent a significant portion of heat gain in hot climates. To assess the thermal and energy performance of This study had three main objectives. First, to assess the thermal and energy performance of hollow concrete block walls, both with and without polystyrene insulation. Second, to compare the annual heating, cooling, and total energy consumption of these systems against the traditional fired clay brick system, which is widely used in Iraq. Third, to model and simulate a typical two-story, 200 square meter residential building in Al-Umara city using the EQuest simulation software and quantify the impact of wall construction on the building energy loads. Okay, in this research, we investigated three wall configurations. First, the traditional fired clay brick wall, which served as the base case. Second, the hollow concrete block wall without insulation. And third, a hollow concrete block wall filled with polystyrene insulation. For materials, the hollow concrete blocks used had a thermal conductivity of 0.13 watt per meter centigrade and a density of 500 kilogram per meter square. Kilogram per meter cubed. Polystyrene insulation was added to the hollow cavities to improve thermal resistance. These configurations reflect actual construction practices in العمارة, making the result directly applicable to real residential buildings. Okay. The simulation was performed using eQuest, which is widely used for detailed building energy modeling. Because the available Iraq weather file in the software only represent Baghdad and its climate difference from العمارة, we selected the Kuwait climate file, which better represent the higher temperature, humidity, and solar radiation typical of العمارة city. The key simulation parameters were the cooling set point was 25 centigrade, and the heating set point was 20 centigrade. And the heating set point was 20 centigrade. The infiltration rate was 0.35 air change per hour. The HVAC system coefficient of performance, which called COP, is 2.9. This setup ensures consistent, realistic, and comparable results across all wall systems. Now let's move on to the building model. The building model represents a realistic two-story family house of 200 square meters, a common found in العمارة city. The key geometry and structural features include a floor dimension of 10 by 20 meters, a total structure height of 6 meters, and the structural alignment is southern orientation, and the structural alignment is southern orientation of the front elevation. Also, a single pane window with 1% to 13% window to wall ratio was used in the building. And also the model was divided into thermal zones and simulated hour by hour for an entire methodological year, for an entire typical year. Now let's move on to the result. Here we see the monthly total energy consumption for the three systems. For the traditional brick wall, the peak value was in August with 5.28 megawatt hour, as expected due to the extreme summer temperature, and the lowest energy usage was from March to December. For the uninsulated hollow concrete block, the peak in August decreased to 3.89 megawatt hour, and the lowest energy also occurs in February, March, and November. For the insulated hollow concrete block, the maximum monthly energy consumption for the insulated hollow concrete blocks, the maximum monthly energy consumption decreased in August from 3.89 0.98 to 3.52 megawatt hour. In all systems, the lowest energy consumptions occur the lowest energy consumption occurred during March and November, when the temperatures are mild and the HVAC system are used minimally. Okay. Okay, here is the breaking down of energy consumption by end user category to cooling and heating and other energy usage. In first case, for the common fired clay brick wall, we can see here the cooling accounts for 58% of annual energy use, which is about 18.82 megawatt hour, and the heating represents 10%, which equals to 3.15 megawatt hour. And for the second case, the HCP without insulation, the cooling decreased to 54% instead of 58%, and the total consumption decreased to 13.67 megawatt hour. Also, the heating decreased to 7%. And the final case, the hollow concrete block filled with polystyrene thermal insulation, where the cooling drops to 52%, which is approximately 11.78 megawatt hour, and the heating consumption decreased to 60%, which equals to 1.44 megawatt hour. These results clearly show that adding polystyrene significantly improves the thermal behavior of the wall, reducing both the cooling and heating loads. Now let's move on to the conclusion and the future work. Based on the simulation, the installation of the hollow concrete block system achieved the lowest peak energy consumption, which equals to 3.52 megawatt hour in August, compared to 3.89 megawatt hour for uninsulated HCP and 5.28 megawatt hour for a traditional brick wall. And also the annual energy saving were 29.4% for insulated HCP compared to brick, and 16.08% for uninsulated HCP compared to brick, which is the common case. These findings confirm that strong thermal advantages of filling hollow concrete block cavities with polystyrene, and given the hot climate of southern Iraq, characterized by long cooling seasons, this system provides a reliable, cost-effective, and practical solution for improving residential energy efficiency. And for future work, we recommend performing a full economic feasibility analysis, a life cycle, also a life cycle environmental impact assessment, and potentially experimental validation. Okay, that's it. Thank you very much for your attention and for attending this session. I would like to express my appreciation to the conference organizers and my co-authors for their contribution to this work. I will now be happy to answer any questions from the committee or from the audience. Thank you.